Al Marifa International Private School, IGCSE Physics, 0625 Thermal Physics. Evaporation. Evaporation happens when more energetic molecules near the surface of a liquid escape. When this one happens, energy is lost from the liquid. So the average of energy of the remaining molecules decreases. As you see, these two molecules in this figure, they are the most energetic molecules. So since they have the highest energy, they can escape from the surface. And this is called evaporation. This means that the temperature of the remaining liquid will also decrease. Question 3. When a liquid evaporates, some molecules escape from its surface. Use these words to discuss which molecules escape and how this change the temperature of the remaining liquid. The four statements. First one, high energy molecule. Second one, low energy molecules. Third one, temperature increases. Fourth one, temperature decreases. The answer. The high energy molecules near the surface of the liquid have enough energy to escape from the surface, or we can say overcome the intermolecular force between the liquid molecules. When the high energy molecules escaping from the surface of the liquid, the average energy of the remaining molecules reduced. So we can say that the temperature of the remaining liquid decreases. We have four factors affecting evaporation. First one, temperature. Second one, surface area. Third one, humidity. Fourth one, wind speed. Factor number one, which is temperature. Look at this container. This container is exposed to high temperature. This container is away from the high temperature, the source of light. That's why these two arrows represents that the evaporation of this container is less than the evaporation of this container. So as you see, since we have here three arrows, so the evaporation rate for this container is more than the evaporation rate for this container, since the temperature of the first container is more than the temperature of the second container. So the temperature and rate of evaporation, they are directly related to each other. More of temperature, more of rate of evaporation. Less of temperature, less rate of evaporation. Second factor, surface area. As you see in this container, the surface area is less. In this container, we have more surface area. These three arrows represents that when the surface area increases, the rate of evaporation is more. These two arrows represents that when the surface area decreases, the rate of evaporation also decreases. So the relationship between surface area and evaporation is direct. When we have more of surface area, more of evaporation, less of surface area, less of evaporation. Third factor, humidity. As you see here in the two containers, we have open one and closed one. So as you see, the humidity of the closed one is more than the humidity of the open one. That's why we represent the evaporation by two arrows here, and the evaporation here by three arrows. So when humidity is more, evaporation rate is less. When humidity is less, evaporation rate is more. So as you see, humidity and evaporation, they are inversely proportional. So when we have more of a humidity, we have less rate of evaporation as the container one. When we have less humidity, we have more evaporation as the figure in the container two. Fourth factor, wind speed. As you see, the red container here is exposed to a fan, and there is speeds currently here. So as you see, the evaporation that represents by 3 arrows is more, while this one that is far from the fan, the evaporation represents by 2 arrows. It means where we have more current speed of air, so we have more of evaporation. Where we have less speed of air, so we have less evaporation. So when the speed and evaporation are directly proportional to each other, more speed of air, so more evaporation, less speed of air, less evaporation. More of explanation of these factors. So we have 4 factors affect evaporation. First one, the temperature of the liquid. At a higher temperature, more molecules have enough energy to escape. Second one, the surface area of the liquid. If the liquid has a greatest surface area, there will be more area for which the molecules can escape. Third one, the movement of air across the surface of the liquid. The presence of a draft can help to remove less energetic molecules, which might not have quite enough energy to escape from the liquid. The process of evaporation can be used to cool things down. If an object in contact with an evaporating liquid, as the liquid cools, the solid will cool as well. This process is used in refrigerator and an air conditioning unit. Question number 4. 3 beakers containing different amount of same liquid. So we have different amount of same liquid at same temperature are left at the school lab overnight. The beakers are stored next to each other. In which beaker does the greatest quantity of liquid evaporate? Justify your answer. So A, B, C. The answer, the temperature of the 3 liquids is the same, so no effect of evaporation. Second one, the amount of air across the 3 liquids is the same, no effect on evaporation. In beaker C, the greatest surface area, and so will the evaporation will be the most. Again, as you see, the surface area of the C is the greatest, so the evaporation for the beaker C will be the highest, since same liquid and same temperature, so the effect will be only for the surface area. Since C has the greatest surface area, so the greatest rate of evaporation. Now, boiling and evaporation. We have now to discuss what are the differences between the process of boiling and the process of evaporation. This container here represents evaporation, and this container here represents boiling. Now, as you see in evaporation, bubbles cannot be formed since only the surface molecules evaporate. So in boiling, bubbles can be formed since all of the molecules they are sharing in boiling. Now, evaporation takes place only at the surface. Second, evaporation takes place at any temperature. So in evaporation, at any temperature, we will have evaporation. And the molecules that are sharing in evaporation, only the surface molecules, the most energetic molecules from the surface. In boiling, it takes place only at boiling point, and also takes place within a liquid and on its surface. So all molecules in the container of the boiling side, all of them sharing and boiling, while in evaporation, only the surface molecules. In evaporation, it happens at any temperature. In boiling, it happens at a specific temperature, which is called boiling point. In evaporation, we don't have bubbles. In boiling, we have bubbles. So these are the main differences between evaporation and boiling. Now, we have here in more details, we have more of differences between evaporation and boiling. The extra one here, that the boiling is a quick process. Evaporation is a slow process. The one that here also, that the thermal energy supplied by an energy resource. Here the thermal energy supplied by the surrounding. So these are the two, number 2 and number 6, they are the extra differences between boiling and evaporation. Now, pressure, temperature, and temperature. We said that the molecules in a gas move around randomly at a high speed, colliding with surface and exerting pressure upon them. Gas molecules collide with surface exerting a pressure. When the temperature of gas is increased, the speed of molecules also increased. This caused them to collide harder with the surface, and this is caused to increase the pressure. Increasing the temperature of gas caused to increase the pressure. So temperature and the pressure are directly proportional to each other when the volume is fixed, when the volume is constant. Now, see this question. A sample of a gas is kept in a sealed container. The temperature of the gas is increased. Which of the graphs here shown below best represents how the pressure of the gas changes with the temperature? Justify your answer. As you see, we have A, then we have B, C, and D. Which one do you think the line that exactly represents the relationship between pressure and temperature at a constant volume? Now, the container is sealed or closed, so we can say that it is contain a fixed volume of gas. Graph B and D are not correct. Pressure increases with temperature, and this is incorrect or not correct because the pressure increases with temperature. Graph C also incorrect, as the gas cannot have zero initial pressure, so it is not correct. The answer is A only. Why? Because as the pressure increases, also the temperature increases, so they are directly proportional. And the pressure does not have zero value at the beginning. I will return back here. So the answer will be A. A is the right one, since pressure and temperature are directly proportional to each other, and the pressure at the beginning does not have a zero value. It has some value at the beginning. While B is constant relation, and this is incorrect. D is inversely relation, and this is incorrect. C is incorrect because the pressure starts from zero, and this is impossible. It must have a value. Now, Boyle's law. If a gas has an original pressure P1 and volume V1, then its final pressure and volume P2 and V2 will be given by this relation. So if you keep some amount of gas in a container, which it has originally some pressure, which is P1, and some volume, which is V1, and you start to increase or decrease its pressure. So the multiplication product of the pressure 1 and V1 will be equal all the time to the multiplication product of the pressure 2 and the volume 2. And this relation is given by this formula. So this is the Boyle's law. The product of multiplication of the pressure and volume before is equal to the pressure and volume multiplication after change. So P1 times V1 is equal to P2 times V2. So the above equation, which is this one, is only works if the temperature of the gas remains constant. So the relationship between pressure and volume is directly proportional to each other. The multiplication product of P1 V1 is equal to the multiplication after of P2 V2. But this formula is working only if the temperature is constant. Now, more details about the relation of pressure and volume when the temperature is constant. Now, when a gas is compressed, as seen in this figure here, the density of the gas increases. When a gas is compressed, it becomes more dense, increasing the pressure. So the molecules will start to hit the walls of the container with more force per unit of area. This means there will be more collagen against the surface, which will also increase the pressure. So decreasing the volume of the gas will increase the pressure. And the opposite is right. As you see, when you hold the piston up, the volume increases. As well, the collagen with the wall will be less. So when the volume increases, pressure decreases. When the volume decreases, pressure increases when the constant is same. But the product of multiplication of P1 V1 will be equal to the product of multiplication of P2 V2, and this is Boyle's law. Now, what is thermal expansion? Now, when most of the material are heated, they expand. This expansion happens because the molecules start to move around or vibrate faster, which causes them to knock into each other and push each other apart in all directions. That's why thermal expansion happens for liquids, solids, and gases. Now, when a solid is heated, the molecules vibrate more, and this is caused to push the molecules each other far away, and this will cause the thermal expansion. But note here that when this happens, the spaces between molecules will be more. The molecules themselves will remain same size, but the intermolecular distance between them will increase. Intermolecular distance between them will be more. Thermal expansion of solids, liquids, and gases. Now, all of the three states, they expand and contract. Expand when they heated up, contract when they cool down. Now, we have differences between the expansion of solid, liquid, and gas. So when the temperature of any material is increased, the speed and kinetic energy of its molecules also increased. This causes the molecules to be pushed farther apart, and the material expands slightly in all directions. When the material is cooled also, the same process happens, but in an opposite way, which is called contraction. Now, in solids, as you see here in solids, the molecules have strong bonds between them, so they have the smallest expansion rate. Now, the liquids. you know that the liquid molecules bond or intermolecular force is less than solid or weaker than solids. So also they expand, but the rate of expansion of liquids is more than the rate of expansion of solids because the intermolecular force of liquid is weaker than solids. In gases also expand in very big rate since they have the weakest intermolecular force. So gas molecules have very weak intermolecular force. That's why they have the greatest intermolecular, the greatest expansion rate. Now, the material can be expanded in length, in size, in diameter, in any shape. Now, expansion and contraction of material. So in contraction, the average energy or average of kinetic energy of temperature of the particles now decreases. So the spaces between the particles, as you see here, the spaces or the intermolecular distance decreases. So matter in the liquid, solids, and gases, also all of them, they contract in same way. In expansion process, the average of energy or temperature increases. So the spaces between the particles or the intermolecular distance between the particles increases. So by this way, we can say that the material expands. The applications. First application we have is bimetallic strap. The bimetallic strap consists of two straps of different metals. First one, the upper one, is called brass. Down one is called iron. Now we have two metals from two different material. First one, upper one is brass. Second one is iron. They have different rate of expansion and contraction. As you see here, when the temperature is less, the contraction of them will be upward. When the temperature is more and they got hotter, the expansion will be downward, curved downward. Brass all the time expands more than iron when it is hot and contracts more also. For example, these two straps or bimetallic strap is used inside thermostats or even thermometers. And this will help to open the circuit of the thermostat or close the circuit as the two straps contract or expand. So this tool will help to control the electrical circuit of thermostat or other application. See the application also of fire alarm. Here are the bimetallic strap. See how the bimetallic strap is used inside the fire alarm to close the circuit and to produce a sound to announce that there is fire. Now, more of details about applications. One of the first important application is thermometer. As you see, the liquid that is used inside the bulb of thermometer, which is mercury or alcohol, is using the thermal expansion idea or thermal contraction idea. Now, when you suspend this one in a hot object, so this will help to expand the mercury to show how much is the temperature of that object. And as well, if you suspend the thermometer inside a cold object, the mercury will contract to show you how much is the decrease in temperature. So the thermometer is one of the application of thermal expansion. Look here, also we have the bimetallic strips that we discussed before. Now, liquids, expansion and contraction. In liquids, expansion, we have important note that liquid level first falls, then raise when a flask is plunged into a hot water. Now, this idea, why? Because the liquid inside will firstly contract, then it will expand when you suspend it in a hot water. The reduce in the level of the liquid inside the beaker here will be because of the contraction of the expansion of the container. So because of the expansion of the glass of the flask, so the temperature of the liquid decreases. This is well shown by decreasing in the level of the liquid at the first when you put the beaker or the flask on a fire or on a hot water. So as you see, the solid or the glass will firstly expand, then that's why the temperature of the liquid decreases. So the level of it decreases. So by this way, after expansion the flask glass, the liquid inside the flask will start to expand again. But at the beginning of putting this flask on a fire or on a hot water, the level of water will decrease, then increase. Why? Because the container firstly will expand, then the liquid. Now, expansion of liquids. All liquids expand as we explained before, on heating and contract on cooling. Immediately, the level of the water drops as the flask expands first. So because the flask or the container expands first, so the level of the water drops at the beginning. But after, the level of water will start to raise up. Why? Because it will start the process of expansion. So as you see, the expansion of the water will be more than the expansion of the glass. But as we said before, the expansion of the glass will be the first. Now, look at these beakers. We have different types of liquids. We have, return back to our slide. Yes, this one. So as you see in this container, we have water and we have ether in this one, benzene in this one, alcohol. As you see, all of them, they have same volume of liquid and they are exposed to same temperature. Look at the expansion rate of this liquid ether. It is the most. Then this one, then this one. So as you see, the expansion rate of every liquid is different from other one. So for every type of liquid, we have a specific amount of expansion rate differ from other one. Now, the expansion of liquid. Now, as you see here, we have liquid water and we have ice water. Now in physics, we have exceptions. This is one of the exceptions. We said that all liquids expand, increase in size when they heated up, and contract, decreasing in size and volume when they cooling down, when their temperature decreases. For water, the case is opposite. As water freezes, the hydrogen bond push the H2O molecules farther apart from each other, increasing the intermolecular space, resulting in expansion. So as you see, the hydrogen bond increases when the liquid water freezes and become ice. So the expansion happens here in opposite way. When liquid water changes into ice, so the volume of ice or of the material increases, so the expansion happens. Now, as you see here in the cup, we have ice and water. As you see, the ice is formed because of a freezing, and as the result, the ice float upon the water. Since it expands, its density decreases, and as well, it starts to float upon the water. So, the exception in physics that water expand when it is freeze and become ice because of this unique characteristic in hydrogen bond between the molecules of water. Now the relationship between density and thermal expansion, thermal contraction. Look at this container. In this container, we have fixed container in the three figures here. Inside this fixed container, we have contraction of molecules. As you see, when they contract, the intermolecular distance decreases. So in same volume, I will have more amount of substance. I have more mass. So as you see, more mass in first container cause to have more density. So as you see, when I have contraction in first container, so I have more density. Now, if you heat this container up, the molecules start to expand. The intermolecular distance increases. So in same volume, you will have less mass. So less mass means less density, since D is equal m over V. So the density decreases. If you keep heating up this container, so the molecules will expand more. Intermolecular distance increases more and more. So in same volume, I will have less amount of substance. So I have less mass. So the density decreases, and also D will be equal m over V. So as you see, when a material or a fixed volume expands, its density decreases as its mass decreases. And if a fixed volume contract, so its density in same volume will be more because the amount of molecules in a specific volume, 1 cubic centimeter will be more mass in 1 cubic centimeter, so the density will be. So the relationship between density and expansion, density decreases when expansion increases, and density increases when contraction increases. This is the relationship between density and thermal expansion, thermal contraction. Thank you.